Hey everybody, we're going to take a look at the big five theorems of calculus. And we're actually going to look at the first four. We'll save the fifth one for when we get there later in the year. The first theorem right here is the extreme value theorem. It tells us that a function is continuous on a closed interval, a to b, so therefore f must have both a maximum and a minimum on the interval. This is the absolute extrema theorem. We've already covered it, so let's look at a graphical representation of it. I've just chosen the first quadrant here to work with, but this graph could extend across quadrants 1 and 2. Alright, let's decide to call this A, and we'll decide to call the end of our interval B. So A and B are x values, a beginning x and an ending x. Okay, and so I'm going to go ahead and just draw a piece of a graph that's continuous. I think it's important to note that right here you can see that it doesn't say that the graph has to be differentiable. So you might want to purposely, because it doesn't say differentiable, you might want to purposely draw a graph that is not differentiable. So I'm going to try and draw a sharp corner here, a sharp turn, and extend this upward in this fashion. Alright, so we have endpoints. And the graph is continuous, but it's not differentiable. So this ordered pair right here would be called a comma f of a, whatever the function is. And likewise, this point here would be our other endpoint b, and the function evaluated at b. So we could find f of a and f of b if we knew what the equation was that we're working with. So over here, we would call this f of a, and then trying to line it up over here, this would be our f of b. So just notation that represents the theorem. Okay, and as we can clearly see on this graph right here that we do have both a min and a max. And the minimum just happens to occur right here. And we'll call this value right here, this x value c. So if we wanted to name this point, we could name it c comma f of c. Alright, so this theorem tells us that we have both a max and a min. Well, our minimum occurs at x equals c. Our maximum appears to occur at an endpoint, x equals b. So we could have a minimum and a maximum occur either at a critical number or an endpoint. And that's the extreme value theorem. Alright, let's take a look at the intermediate value theorem, paying attention to the if statement. And again, you can see that they told us that we need to consider a function that's continuous but not differentiable perhaps on a closed interval. And then it tells us k is any number between f of a and f of b. Well, these are two y values right here. So let's go ahead and get an illustration of that. And I'm just going to go ahead and pick on the first quadrant again. Here's a, here's b. And I'm going to go ahead and just draw a piece of a graph that's continuous. As a matter of fact, I'm going to pay attention to the fact that it doesn't say it's differentiable. So in that case, instead of a sharp turn, this time I'm going to draw a vertical tangent. So we can see right here that probably at this point right here, the tangent line is vertical, so we would say that this graph is not differentiable at this x value right here, but it's certainly still still continuous. Okay, so let's look at the endpoints here. So again, this is a f of a, and likewise this point would be b f of b. Alright, and this theorem tells us that if this is true, which we've drawn a graph that satisfies the if statement, there has to be at least one number c in a to b, that small x to that big X, such that f of c is equal to k. Alright, so for this particular function right here, and for this theorem, we need to pay attention to the fact that here we have our y values, f of a, and if you kind of line up horizontally here, it appears that our y value for b is right here at f of b. So this theorem tells us that if this is all true, that somewhere between these two y values there has to be a k that falls in between here, such that my c value is going to fit in between a and b. So no matter what k value you choose in between here, for example, if I call this k, I should be able to go across, hit the graph, and then at this point drop down and call this c. So this point right here would be called f of c, oh excuse me, this point right here would be called c f of c. Let me try and label this again. I'm going to make this a c, comma, f of c. But as you can see, this f of c y value would be equal to this k right here. So basically what this is saying is that if I have a continuous curve from this endpoint to this endpoint, that no matter what y value I choose between these two y values, I should be able to intersect the curve. And that's because there's no way I can go from here to here without passing through every y that falls between f of a and f of b. So that's the intermediate value theorem. All right, let's look at Rolle's theorem. Okay, now notice that it changes a bit. The function has to be continuous and differentiable. The function has to be continuous on the closed interval from a to b, but it's going to be differentiable on the open interval from a to b. So I want to exclude looking at the endpoints for differentiability. All right, and then it also tells us that f of a must equal f of b. So what that means is that if I were to begin my graph here, no matter what I did, okay, if I drew it up and then down and then up and then back down, that this y value right here at the other endpoint, this f of b value if you will, right, it has to be the same y value as this y value at a. So f of a equals f of b. So right here I could say that f of a equals f of b. So those are the given conditions for this theorem, Rolle's theorem. So if f is continuous, which it is, on the open interval from a to b, and it's differentiable on the, if f is continuous on the closed interval from a to b and differentiable on the open interval from a to b, that there is at least one number c that falls between these two x values such that the slope of the graph is 0. And this is supposed to be more rounded than it looks right here, but we're supposed to have at least one number c such that the slope is 0, where you have horizontal tangents. So we can see that right here, that perhaps if this is more rounded and more smooth, that if I were to draw the tangent line through that point, okay, the slope would be 0. So that would be one of our c values at which that occurs. So right here, we could say that f prime at c sub 1 equals 0. All right, let's look at this point right here. It appears that there's another place on this graph from a to b where the slope is also 0. So maybe we'd call this c sub 2. So we can see that the slope at c sub 2 is also equal to 0. And it appears that there's another place where we also have a horizontal tangent, and that would occur about right there. We have to have at least one spot on the graph. There could be more. There could be an infinite number where the slope of the graph is 0. So we could call this c sub 3. So f prime, the slope at c sub 3, is also equal to 0. Alright, so we're guaranteed if the endpoints have the same y value, and just think about that. If the endpoints have the same y value, let me change colors here. If I drew straight across from one endpoint to the other, look at the average rate of change from A to B. The average rate of change, okay, is 0. The slope of that secant line is 0, if you will. So if the slope is 0, there's got to be at least one other place on this graph, if the graph is continuous and differentiable, at which the slope of the graph is also 0. And in this example, there are 3 locations. Before we move on to the fourth and final theorem we're going to look at, I want you just to think about what if. What if I had drawn originally this graph, if I had drawn just a straight line, like this red line here. If I just drew a graph from this endpoint to this endpoint straight across, think about how many times the slope of the graph along the path from the open interval to from A to B, think about how many times the slope of the graph would be equal to 0. Well, that would be every single c value that exists between A and B, because the slope of the secant line is 0, so the slope of the graph anywhere along the way would also be 0. That's kind of a special case. likely you're going to see something like this right here. All right, let's look at the mean value theorem for derivatives, the fourth one. Again, f is continuous on a closed interval and differentiable on an open interval. So we're going to go ahead and draw something similar to what we had here. But this time I don't want my y values at a and b to be at the same location. So perhaps I might start up here. So this would be f of a. And I'm going to journey on my way over here somewhere when x is b. Remember, it has to be differentiable. So I might start by going down, I might go up, come back down, and then kind of finish like this. So we have the endpoint b, f of b. And if I think about traveling across horizontally, it appears that f of b is about right here. That's a b. And this ordered pair is a, f of a. Okay, so f is continuous, yep, and differentiable, yep. There exists at least one number c in the open interval from a to b such that the slope at that c value on the graph is equal to this expression right here. Well, if you think about this expression, this is actually just delta y over delta x. It's a change in y over change in x from the left endpoint to the right endpoint. So let's kind of get a graphical representation of f of b minus f of a over b minus a. It's actually just the secant line through these 2 points. Okay, so similar to what I did on Rolle's theorem has me have the two y values equal to the same value, but here my fa and my f of b could be 2 different values. So now notice that this line, this secant line, doesn't have a slope of 0. It appears to be some negative number. I don't know what that is because I don't have a function to work with, but it appears that the slope of this secant line is negative because the line is falling, it's decreasing. So this theorem is similar to Rolle's theorem. It just says now, you know what? Somewhere on this graph you have to have another tangent line. You have to have a tangent line that has the same slope as the slope of the secant line. So what we're going to do is we're going to think about traveling along this graph, and at what point would I stop, at what x value, we'll call it c, will I stop, and when I draw in the tangent line is actually parallel to the secant line. And as we remember, parallel lines have the same slope, and that's what this expression is saying right here. The slope of the graph is equal to the slope from one endpoint to the other. Well, we can clearly see that if I drew in a tangent line to the graph right here at this peak, the slope of that line is 0. Well, the slope of that line being 0 would not be the same as the slope of this secant line right here. So it's not going to occur at the mins and maxes for this theorem. Think about traveling along the graph. I'm thinking about right here. The slope of the graph, if I were to draw in a tangent line, would maybe look something like that. So I'm going to call this c sub 1. So right now the slope f prime of c sub 1 is not equal to 0. That line doesn't have a slope of 0. The slope that it has is equal to delta y over delta x. F of b minus f of a over b minus a. It appears that if I were to continue along the graph, that the slope of the graph somewhere else might also have the same slope as a secant line. So I'm thinking once I get past this maximum and I start to decrease on the function, somewhere probably about right here, past the maximum, I would have another tangent line to the graph whose slope is the same as the slope of the secant line. Just kind of work with me and see that maybe this line right here, tangent line, is parallel to the secant line. They have the same slope then. And so I've just now located the c value on the graph at which the secant slope is equal to the tangent slope. So again, f prime of c sub 2 doesn't equal 0, but it does equal delta y over delta x, the change in the y's over the change in the x's. Is that the only other place besides c sub 1 at which the slope of the graph is the same as the slope of the secant line? No. Keep traveling, keep traveling. It appears that maybe somewhere about right here, the tangent line to the graph is again parallel to the secant line, so I could call that C sub 3 and continue along the same way I did with these other two. And it appears that there might even be one more location at which the slope of the graph is the same as the slope of the secant line, so I could call that C sub 4, if you will. So this theorem guarantees that if you have a differentiable curve on an open interval, that you're going to have at least one C value that falls between A and B, such that the tangent line is parallel to the secant line. So all kind of abstract, especially these last two. So in the next video, what we're going to do is a couple of examples of each of these theorems. I think the first two are pretty straightforward, the two theorems here. At least the first one we've already practiced when we did the absolute extrema lesson, and we created the t-chart by putting the candidates in the x column, the endpoints and the critical numbers, and finding the y values to figure out which one was the min and the max. And this one is pretty straightforward too. We'll look at some examples in the future of how this theorem right here could be asked in certain types of problems. So in the next video, let's just take a look at how we would use Rolle's theorem and the mean value theorem to solve problems.